Well, here we are again. I'm going to do what I hope is a relatively short video that finishes up a little bit about earthquakes and then introduces and discusses volcanoes. I wanted to just one more time emphasize the importance of earthquakes in helping us understand the interior of the earth. And this can be seen in this diagram that I've shown you already of an earthquake, the earthquake shadow zones created by the different phases of matter that have been discovered within the interior of the earth. This liquid outer core of iron and nickel and the interior solid core, as opposed to the solid mantle and then plastic mantle near the surface, have all contributed to creating these shadow zones where if you have a seismogram, you won't pick up, or seismometer, you won't pick up any P waves or S waves. And here is that P wave shadow zone, 105 to 140 degrees away from an earthquake epicenter. P waves deflected or refracted by the liquid. They don't make it down into, they're disturbed in such a way that they don't make it back to the surface. And then of course none of the S waves make it through the liquid at all. So we have these two shadow zones, the P 105 to 140 on either side of the earth, and then an S wave shadow zone from 105 to 105 degrees from the epicenter. I then wanted to just mention that there's another layer that was determined through seismic activity by a scientist named Moho Discontinuity. I don't know how to pronounce his name. A geologist who discovered that there was a point where it's now considered that the crust ends and the mantle, including which is the upper mantle at this point, the plastic mantle, where the crust and the plastic mantle meet, is now known as the Moho Discontinuity. Again, discovered by a geologist of that name, is the boundary between the crust and the plastic mantle. He discovered that P and S waves are refracted at this boundary, thus defining a set of unique layers, crust, mantle. So that then was expanded with our understanding of the liquid outer core, creating another unique zone. So it is through seismicity, our understanding of seismic waves, that we have an understanding of the interior of the earth, an inference, an inferred understanding. This just gives you a sense also of how this Moho discovery is in part discovered because velocity of seismic waves increases abruptly at about 50 kilometers in depth. This tells us that the density of the rocks are changing. The lower layer must be, and in this case we can fill it in, denser because the waves are traveling faster. And so this was an insight that led to this understanding that we have a crust, the Moho discontinuity, and then this new layer, the plastic mantle, underlain by the stiffer mantle, outer core, and finally inner core. And this was just a map that gives us a sense of earthquake hazard in the United States. There is some hazard. You can see we're yellow here because of a particularly famous fault called the Ramapo Fault, which heads from northwest New Jersey across to the northeast. It's located in not quite northwest, central northern New Jersey, and then heads northeast across the Hudson, and actually was far too close to a nuclear reactor called Indian Point, which has recently been decommissioned. And you can see that the whole of New England is higher level than you would think, and that in part I believe is due to the fact that glacial ice has compressed the land, and then over the thousands of years since that ice has left, there has been uplift or rebound. I think they call this isostasy, and that has increased the level of potential earthquake hazard in New England. But of course the greatest hazard is along the San Andreas Fault and in the northwest, where the Juan de Fuca plate is meeting the North American plate. And here we have a transverse plate motion, with North American plate heading down in this sort of southeastern direction and the Pacific plate moving up. So high levels of potential earthquake activity in that region. And then here is the site thought to be occurring because of the subsidence of rock, I believe, sinking of rock in this region, of what was known as the New Madrid earthquake, which is thought to have been upwards in the 8 to 9 region on the Richter scale, and erupted in 1811, 1812. Occurred. Tsunamis. I'll show you this video of tsunami on Tuesday in class. I don't want to go to videos in this presentation, but I'll show you some tsunamis and some volcano video. But you should be aware that tsunamis occur as a result of an earthquake, or as a result of a sudden movement of undersea sediments on the continental slope. And what can happen is that these sediments will slide down, and they can cause a tsunami. But typical, what we best understand about tsunamis, or the most frequent type of tsunami, would be caused by the displacement of crust on the bottom of the ocean. So a fault, there's a slipping along a fault at the bottom of the ocean, and water is suddenly displaced in such a way that it creates an upwelling that pushes the ocean surface at the site of the quake up higher, and then gravity pushes that upwelling sideways and creates this rapidly, super fast release of energy through the ocean. And once, of course, the wave begins to approach the shore, the bottom of the sea slows the wave down, it begins to push up the bottom, creates a taller and taller wave, which then breaks. And of course, these are unexpected. Until recently, there wasn't a good warning system, and these are the things that you should keep in mind when you are visiting an area, particularly around the Pacific Ocean, the Ring of Fire. If you're near the coast and you feel an earthquake, which you might, you want to drop, cover, and hold, and then get inland, because the tsunami, if the earthquake was near the shore, the tsunami can arrive very quickly. This would be anywhere like Alaska, British Columbia, Washington, Oregon, California, Hawaii. Well, you won't feel an earthquake there, but you can get a tsunami from any of these other active locations. And then on the western coast of the Pacific Ring of Fire, you observe the ocean receding. That doesn't happen all the time, but particularly in the famous 2004 Indonesian tsunami, the ocean went out very quickly, and you could see the bottom of the sea that you normally wouldn't see even at low tide. And in fact, there's a famous story from that tsunami of an English girl, middle schooler, who had been taught about tsunamis before her family went on vacation. And of course, this tsunami in 2004 occurred on the day after Christmas, so it was a holiday, and that's a big holiday place for a lot of people, Indonesia, Bali. And she watched the water recede, saw all these fish flopping about, and ran in and said, "I think there's a tsunami coming." And her family was able to get up high enough in a building so that they weren't harmed. Many people, though, 228,000 people died in the 2004 Indonesian tsunami. Then, so you've observed the ocean receding. Now you observe an abnormally high surge of water coming inland, and I'll show you some video of that. You see odd ocean whirlpools, or hear an unusual sound coming from the sea. The bottom line is that you need to be aware, and we hope now, since 2004, that there is a reliable tsunami warning system throughout the Pacific and Atlantic Oceans. Now we're going to move on to volcanoes. This is a famous shot of the Cleveland volcano in the Aleutian Archipelago, part of the United States, part of Alaska, erupting with smoke and ash. And we want to just learn the basics of volcanoes. It's another example of a force of nature that occurs as a result of plate tectonics. Volcanoes, both the opening in the crust through which molten rock, gases, and ash erupt and flow, and the landform that develops around the opening. Volcanism develops at 3 locations on Earth. 1, where crustal plates, tectonic plates, converge, and one plate subducts, moves under another. This is often 2 ocean plates, or a continental and an ocean plate meeting. That's where you can get subduction. Where crustal plates diverge at mid-ocean ridges, in the middle of the ocean we have areas where the crust separates, and this would also actually be in parts of the Rift Valley of Africa, East Africa we have crustal plates diverging, and the island of Iceland is actually probably the result of this mid-ocean ridge and land that has been created by volcanism where crustal plates diverge. And then over hot spots such as Hawaii, Iceland, and where Yellowstone Park is, areas where otherwise passive areas where there's no activity on a tectonic plate, you find volcanism. Now why? Well, that's because the plate is moving over an area where the magma, where the mantle is pushing up closer to the crust than in any other place in the region. And so you get these hot spots, areas where the surface crust passes over magma, lava pushing up to the surface. And in the case of Yellowstone, you don't see lava, but you see geysers and other signs of this magma chamber below, and it's thought that one day there'll be a gigantic explosion of volcanic activity at Yellowstone. But Hawaii and Iceland have frequent and constant release of magma lava, and we'll look at some videos of that. Here's that subduction. It's creating volcanoes. What's happening? We have an ocean plate made out of basalt running into the Caribbean plate, which may be continental, may also be volcanic, or have once been ocean, and it's the constant subduction here has created the land above. But the bottom line is that you've got subduction here, which melts the ocean sediment and rock, and then that melted material, being less dense, floats up, pushes up through the plate, and creates a zone of pressure that can eventually explode and release lava, which can become new land. This is an example of subduction where ocean crust is going under continental crust along the coast of South America, the Villarrica volcano in Chile. Then we're in the middle of the ocean, and we have diverging plates going apart. And here we can see a volcanic vent under the ocean water in the middle of, the Atlantic. And we call this area the Mid-Atlantic Ocean Ridge, a range of submarine mountains and volcanoes. Where the ridge rises above sea level, islands such as Iceland have been created. Here's the North American plate moving west, the Eurasian plate moving east. Convection currents bringing new melted rock to the surface, magma lava to the surface where it is released, and new ocean crust is formed. So the rock here on either side of the ridge is the same age on either side of the ridge, and it is new rock. Volcanism at a divergent plate boundary in Iceland, and I'll show you some amazing footage of explosive volcanism there, as well as the release and formation of shield volcanism in Hawaii. Here again is our famous tectonic plate map, and we were just looking at Iceland divergent and the Mid-Atlantic Ridge. Well, you can see this is where Iceland is, and this is where we have volcanism under the ocean. Only at Iceland has enough material been released from within the asthenosphere that you formed land. But you also have, you'll notice, a place called the Canary Hot Spot, Canary Island Hot Spot, St Helens Hot Spot, Bouvet Hot Spot, Easter Island Hot Spot, Galapagos Hot Spot, Hawaii, Yellowstone. And it says down here, not all mantle hotspots are even shown. So there are these places where, for instance, Hawaii, it right smack in the middle of the Pacific Plate where there shouldn't be any naturally occurring volcanism or earthquake activity, there is a constant flow of lava that has created over millions of years a series of islands. So here would be a picture from a fairly recent release of lava, and then we have this diagram, which is a little bit hard to follow, but let's take a look. Here we have a mantle plume of lava, magma, lava and magma then lava as it gets to the surface, pushing up, and it's released on these volcanoes, Mauna Loa, Kilauea, and Lohi. I don't know if I pronounced that right. And all of that's been happening for the last 700,000 years, that there's been volcanic activity. Meanwhile, the Pacific Plate's been moving. And eventually, this section of the plate will pass over this plume and will be inactive, just as Maui is inactive, Molokai is inactive, Oahu is inactive, Kauai is inactive, and going all the way up towards Alaska, we find a series of inactive volcanic mountains, undersea mountains, that were formed when that section of the plate, the Pacific Plate, slowly passed over this Mantle Plume hot spot. And you can see, here it is, not everything is above sea level, so some things are below sea level, but there's enough that is that we can trace. We could trace it from those alone, and then now that we have good maps of under the water, you can see it there too. This would be pictures of that lava flowing into the sea, which produces actually a beautiful form of basalt called a pillow basalt, when lava flows into the ocean and is cooled rapidly. Let's do the parts of a volcano. So the magma chamber is the source of all. Melts through layers of the Earth's crust, then pushes up with enough pressure, particularly if the conduit, the neck, is blocked at times by rock or lava that freezes up here. You can build up pressure, which then can release or cause an explosive volcanic activity. Lava then flows down, and you can see what we have here in a composite volcano are these layers of activity. Each light, dark, or dark light, dark light, dark light is a period of activity with unique time stamp, as it were. Not necessarily linear. And then you see a branching pipe with a sill that might explode out of the side, a dike which might explode out the side of what they call a parasitic cone, the flank, which has this steep angle of repose, we know, which then can allow the flow of lava and ash and mud, in some cases, to be extremely rapid. So you can't really outrun that. Three types of volcanoes. We have our shield, non-explosive, associated with basaltic lava, broad and low-lying Hawaiian hotspot. Cinder cones. Molten lava explodes into the air from a vent. Lava freezes and lands around the vent, building a cone with a steep angle of repose. There's a beautiful example of this, Mount Bachelor in Bend, Oregon. Composite, built of materials from successive explosive eruptions. The famous Mount St Helens in Washington State that exploded in 1950. Here's your shield volcano in Hawaii, this shallow slope, constant release of lava. But here, these smaller cinder cones, where there was some explosive activity on the flanks of the shield, which then led to this area collapsing on the inside and then cooled lava building up the flanks. Here's another picture of a cinder cone. There are lots of good examples of cinder cones in the west of the United States of extinct volcanism, and then down into Mexico there's some amazing ones. Here's Mount St. Helens, the original Helens, the exploded Helens, and you can see huge chunk of the mountain was thrown into the air. 1.5 feet of ash fell on Portland, Oregon. And here's a beautiful picture by a former teacher here at Booker T, Mr. Bonino, who who took this with its Helens with a dusting of snow on it. I actually have some good pictures of it too. I should actually scan them and put them in. I went there in probably about 1990. Volcanism makes new crust, or volcanoes make new crust. It can make granite with minerals that have low melting point, can form it at a depth of 30 to 60 kilometers. More viscous and so does not rise to the surface very quickly. Cools slower and therefore solidifies underground rather than reaching the surface. Intrusive, coarse-grained igneous rock. So your continental crust is generally not associated with volcanism, whereas your oceanic crust and your volcanic rock is typically basalt or a rock similar to it. There are other types of volcanic rocks, diabase, andesite. So basalt with minerals having a high melting point forms between a depth of 100 and 350 kilometers, more fluid, rises more quickly, cools faster, and therefore reaches the earth as lava and solidifies outside. Extrusive, fine-grained igneous rock. And then we have different types of, again, I mentioned different types of lava which create different rocks: basalt, andesite, dacite, I don't know how to pronounce that actually, and rhyolite. And you can see that there's a silica content that varies, SiO2. There's the temperature of eruption, so highest with basalt, lowest with rhyolite. Low resistance, thin, runny lava, highly viscous with the rhyolite. And that gives you get more information down here, low viscosity. There's also this aspect of the chemistry of the lava where we talk about whether it's acidic or basic, which you'll learn about more when you go into chemistry in 10th grade. The basaltic produces wide and extensive landforms with low slopes. The andesitic and acidic produces steep-sided cones. So this would be your composite volcano. This would be your shield, your basaltic shield, your andesitic composite. Lava and steam eruptions with your basaltic, your ash rocks, gases, and lava ejected pyroclastic flows. Pyroclastic means fiery fragments are flowing out of the volcano. Found at destructive margins to produce subduction zone and island arcs. So this is how we get new land where there's subduction. So the island of Japan is a product of this kind of volcanism. And they're infrequent. The basaltic can be frequent, but they're not as explosive. And I think with that, we are done.